For the last 15 years, the entire electric vehicle industry has been quietly hostage to one element on the periodic table. Every EV battery pack, every phone, every power tool, all of it has depended on lithium, a metal so unevenly distributed across the planet that more than half of the world's usable reserves sit in just 3 countries, and prices for it have swung wildly enough to make or break entire car companies almost overnight. In February 2026, lithium carbonate prices jumped more than 10% in a single day after a major African exporter suddenly suspended shipments. That is the kind of fragility an entire industry has been quietly building itself on top of. And in the middle of 2026, the world's largest battery manufacturer put a passenger car on sale that does not need a single gram of it. The car is called the Changan A06, and underneath its hood sits a battery pack from CATL, the Chinese company that already builds more EV batteries than any other manufacturer on Earth, using a chemistry built almost entirely from sodium instead of lithium. Sodium, the same element sitting in a box of table salt in your kitchen cabinet right now. This is not a lab prototype or a limited pilot program. It is a real production car, sold through a mainstream Chinese automaker's dealership network, backed by the company that essentially defines what mass production means in the battery industry. To understand why this matters, you have to understand just how strange it is that an alternative took this long to reach the road at all. Sodium is not some exotic material scientists stumbled onto recently. Chemists have known sodium could theoretically work in a rechargeable battery since the 1980s, around the same time lithium-ion research was getting started, but lithium won that early race and never really looked back. And for 30 straight years, almost nobody seriously funded sodium as anything more than an academic curiosity. It took a genuine supply crisis, not a lab breakthrough, to change that math. By the end of this video, you will understand exactly why lithium has dominated batteries for 30 years, how sodium finally caught up enough to matter, and whether this actually threatens lithium's grip on the EV industry or just gives it, for the first time, real competition. If you like videos about the technology quietly reshaping how the world works, hit like and subscribe so you do not miss what is coming. Let's start with the problem sodium was actually built to solve. Lithium's dominance was never really about lithium being the perfect element for a battery. It was about lithium being the first element that worked well enough, discovered and commercialized decades before anyone had a serious alternative. Once lithium-ion batteries proved themselves in laptops and phones through the 1990s, and then in electric cars starting around 2010, the entire global supply chain, mining operations, refining plants, cathode factories, battery gigafactories, all of it, got built specifically around lithium chemistry. That created a problem nobody fully appreciated until demand exploded. Lithium is not particularly abundant, and the deposits that are economical to mine sit overwhelmingly in a handful of places. The so-called lithium triangle across Chile, Argentina, and Bolivia, plus Australia's hard rock mines, with China controlling the vast majority of global refining capacity regardless of where the raw ore actually comes from. Roughly 85% of the world's usable lithium supply runs through that narrow set of countries and companies, which means a mine closure, an export policy change, or a single country's political instability can ripple through the price of every EV on the planet within weeks. That concentration shows up directly in the price, and the price has been genuinely chaotic. Lithium carbonate prices swung by nearly the entire range from $6,000 to $80,000 per ton between 2020 and 2023 alone, spiking to roughly 150,000 yuan per ton in China during the 2022 peak, before crashing through a 2-year oversupply glut in 2023 and 2024, and then surging again through early 2026 on renewed demand forecasts and a sudden export suspension out of Zimbabwe, one of Africa's largest lithium producers, which had shipped more than 1 million tons of lithium concentrate the previous year, mostly to China. Lithium typically makes up somewhere between 20 and 25% of the total cost of an EV battery pack, which means every one of those swings ripples straight through to what a car actually costs to build, and by extension, what it costs a customer to buy. It also creates a strange, lopsided profit structure across the industry. When lithium prices spike, the mining companies sitting on the raw material can post gross margins north of 50%, sometimes touching 90%, while the battery manufacturers actually doing the manufacturing get squeezed in the middle, watching their own margins compress from around 20% down to the low teens in the same stretch. For a battery manufacturer trying to plan production 5 years out, or an automaker trying to hold a price point on an affordable EV, that kind of volatility is a serious structural risk, not just an inconvenience, and it is exactly the kind of risk a company the size of CATL has every incentive in the world to insure itself against. Sodium looks, on paper, almost suspiciously like the answer to exactly that problem. It sits directly above lithium on the periodic table, meaning it behaves chemically in a very similar way, moving back and forth between a battery's two electrodes to store and release energy through essentially the same basic mechanism lithium-ion batteries already use. But sodium is somewhere between 1,000 and 1,200 times more abundant in the Earth's crust than lithium, extracted from soda ash, the same bulk industrial material used to manufacture ordinary glass, available in massive quantities on every populated continent, with no equivalent of a lithium triangle controlling supply. There is also a quieter but genuinely important manufacturing advantage buried in the chemistry itself. Lithium-ion batteries require an expensive copper current collector on one electrode because aluminum reacts badly with lithium at low voltage. Sodium does not have that problem, which means manufacturers can use cheaper aluminum on both electrodes instead, stripping real cost out of the bill of materials before you even get to the raw sodium itself. Put all of that together, and industry cost estimates put sodium-ion cells somewhere around $55 to $70 per kilowatt-hour to manufacture at scale, roughly 35 to 40% cheaper than a comparable lithium cell once you account for both the cheaper raw material and the aluminum-only electrode design, though those figures still depend heavily on how quickly the sodium supply chain matures compared with lithium's decades-long head start. Sodium cells also come with a safety quirk that sounds small but matters enormously for logistics. They can be safely discharged all the way down to 0 volts for shipping and storage, something a lithium-ion cell generally cannot do without risking permanent damage, which means sodium battery packs can be transported and warehoused with meaningfully less fire risk than the lithium equivalent sitting in the same shipping container today. This is not actually the first time sodium has made it into a Chinese EV, and it is worth being honest about that up front. In February 2023, a small Beijing-based battery startup called Hainan Battery partnered with Seahole, a joint venture between JAC Motors and Volkswagen's Anhui operations, to build a limited test version of the compact Seahole E10X city car running on sodium-ion cells. By January 2024, Hainan and JAC had begun small-scale deliveries of a related model, the Yiwei 3, making it, according to the International Energy Agency, the first sodium-ion-powered electric car to reach the road anywhere in the world. It was a real product, not vaporware, but it was also a modest, low-volume city car from a comparatively small battery player, built more as a proof of concept than a genuine industrial rollout. Sodium-ion battery production globally, even by 2025, still amounted to less than 1% of total lithium-ion output worldwide. That context matters, because it is exactly the gap CATL's launch was built to close. CATL is not a startup testing a concept. It is the single largest EV battery maker on the planet, supplying a meaningful share of every major automaker's battery packs worldwide. And when a company that size decides to commit to sodium at true production scale, the entire calculation changes. The Naxtra program was not a quick pivot either. CATL has said the underlying research and development stretches back roughly a decade, backed by an investment the company has put at around 10 billion yuan, close to 1.4 billion US dollars, long before sodium had any realistic path to a showroom floor. In April 2025, CATL formally launched its sodium-ion battery brand, Naxtra, alongside an announcement that large-scale cell production had already begun, covering both a passenger vehicle power battery format and a separate 24-volt version aimed at heavy trucks. Through the rest of 2025, the company kept pushing the specs forward in public updates roughly every few months, announcing by September that its next-generation sodium cell had reached an energy density of 175 watt-hours per kilogram, the highest ever achieved in a mass-produced sodium battery, enough to support more than 500 kilometers of range in a passenger EV, and that it had become the first sodium-ion battery in the world to pass China's newest national safety standard for EV traction batteries, GB 38031-2025, a certification lithium-ion packs have to clear as well before they are allowed anywhere near a Chinese production car. By December 2025, at a supplier conference in Ningde, Fujian Province, the company confirmed sodium-ion technology would be deployed at commercial scale across multiple sectors throughout 2026, not just automotive. Then, on February 5, 2026, at an event in Yakeshi, Inner Mongolia, billed as CATL and Changan's sodium-ion battery global strategy launch, the two companies jointly unveiled the Changan Nevo A06, the vehicle both are calling the world's first true mass-production passenger car built around a sodium-ion battery, arriving in Chinese dealerships by the middle of 2026. Changan is not a niche automaker experimenting on the side. It is one of China's largest state-affiliated auto groups, and CATL is now supplying Naxtra batteries across Changan's entire brand portfolio, covering Avatar, Deepal, Qiyuan, and UNI, meaning this is explicitly designed to scale across an entire mainstream lineup spanning budget compacts to premium electric SUVs, not sit quietly in one halo model nobody actually buys. The Nevo A06 itself is a compact electric sedan, already on sale since late 2025 in a lithium-based plug-in hybrid configuration, with the new sodium-ion pure electric variant delivering roughly 400 kilometers of range on China's testing cycle at launch, with CATL explicitly targeting 500 to 600 kilometers in future versions as the underlying supply chain matures. The Naxtra cells inside it are engineered to operate across an unusually wide temperature band, from -40 degrees Celsius up to 70 degrees Celsius, and CATL says the chemistry retains somewhere around 85 to 90% of its capacity in extreme cold, compared with roughly 60 to 70% for a typical lithium-ion pack in the same conditions, a genuinely significant advantage for anyone trying to sell EVs into China's northern provinces, Scandinavia, or Canada, all places where cold weather range loss has been one of the most consistent complaints lodged against electric vehicles for a decade. The batteries are also compatible with CATL's existing ChocoSwap battery swapping network, which the company plans to expand past 3,000 stations across 140 Chinese cities by the end of 2026. More than 600 of them specifically in colder northern regions where sodium's cold weather edge matters the most. Here is roughly how the chemistry actually works, in plain terms. Inside both a lithium-ion and a sodium-ion battery, positively charged ions shuttle back and forth between two electrodes through a liquid electrolyte every time the battery charges or discharges, generating the electrical current that actually powers the car. Think of it like two rooms connected by a revolving door, with charged particles crossing back and forth every time you plug in or drive. Sodium ions are physically larger than lithium ions, roughly 1.5 times the size, which for years was assumed to be a permanent disadvantage, since bigger ions generally move more slowly through a solid electrode material and pack less energy into the same amount of physical space, one of the core reasons sodium batteries lagged behind on energy density for so long. What changed over the last several years was mostly on the materials side rather than any single breakthrough moment. Better cathode chemistries, built specifically around sodium's larger ion instead of borrowed from lithium designs, refined electrolyte formulations that let those bigger ions move through the cell more efficiently, and cell architectures engineered from the ground up to work with sodium's slightly different physical behavior. The result is a battery that still cannot match the very top end of lithium chemistry on raw energy density, but has closed the gap enough, while undercutting it meaningfully on cost, safety, and cold weather performance, that it now makes commercial sense for an entire category of vehicle. That category matters, because sodium was never being pitched as a wholesale lithium replacement. CATL itself describes the goal as a dual chemistry ecosystem, lithium and sodium working side by side rather than one displacing the other. Top-tier lithium chemistries like nickel, manganese, cobalt can reach energy densities in the range of 250 to 280 watt-hours per kilogram, noticeably ahead of sodium's current 150 to 175, which is exactly why nobody is proposing sodium-ion batteries for long-range luxury EVs, aviation, or premium smartphones anytime soon. Where sodium makes sense is the enormous cost-sensitive middle of the market. Affordable compact EVs, commercial fleet vehicles, heavy trucks that do not need maximum range, and grid-scale energy storage, all applications where lower cost, wider temperature tolerance, and supply chain stability matter more than squeezing out the last possible kilometer of range. It would be dishonest to end this story sounding like sodium has already arrived as lithium's equal, because the numbers say otherwise, at least for now. Even with CATL throwing its full manufacturing weight behind Naxtra, sodium-ion cells made up less than 1% of total battery production worldwide as recently as 2025, and that share does not flip to anything close to parity with lithium overnight just because one flagship car has launched. The Nivo A06's roughly 400-kilometer starting range is genuinely usable for a city or commuter car, but it is still noticeably short of what a comparable lithium-powered EV in the same price bracket typically offers today, and CATL's own roadmap to close that gap toward 500 or 600 kilometers depends on cathode and electrolyte improvements that are still, by the company's own account, in active development rather than finished. Long-term durability data is also thinner than it is for lithium chemistry, simply because lithium-ion has been sitting in real cars accumulating charge cycles and degradation data since 1996, while sodium-ion in passenger vehicles has only a couple of years of real-world mileage behind it worldwide, and almost none of that mileage has been racked up at highway speeds over multiple full winters yet. Manufacturing costs are also not yet fully settled. Every cost estimate currently circulating for sodium cells assumes the supply chain scales the way lithium's did, with dedicated mines, refineries, and cathode plants built specifically around sodium, and none of that infrastructure exists yet at anywhere near the scale lithium's does after 3 decades of build-out. The 35 to 40% cost advantage often quoted is closer to a target the industry is building toward than a number every sodium cell rolling off a production line hits today. None of that makes the technology fake or the launch a stunt. It makes this the honest starting point of a genuine second battery chemistry, not the finish line. China is not alone in chasing this, though it is clearly ahead. Beyond CATL and Hina, other Chinese battery makers including BYD, Eve Energy, and Ferasis have their own sodium-ion programs in various stages of development, and CATL has already announced that Li Auto, another major Chinese EV maker, will integrate Naxtra batteries into upcoming models beyond Changan's own lineup. Outside China, sodium-ion development exists but trails considerably, with companies like Natron Energy in the United States focused mostly on stationary and industrial storage applications rather than passenger vehicles, and no Western automaker currently has a sodium-ion passenger EV anywhere near production. That gap mirrors almost exactly how the broader battery industry has developed over the last decade. The core chemistry itself is not exclusively Chinese. Sodium-ion research has happened in labs worldwide for years, but the willingness to actually commit tens of billions of yuan and an entire automaker's brand portfolio to scaling it into real, mass-produced cars has, so far, only happened in China. Step back, and the significance of this moment is less about sodium beating lithium and more about lithium finally facing a real competitor for the first time in 30 years. For 3 decades, if you wanted a rechargeable battery light enough and dense enough to move a car, there was effectively one answer, and every automaker, every government, and every mining company on the planet had to build their strategy around that single point of dependency. CATL, the company with more to lose from that dependency breaking than almost anyone else on Earth, just spent a decade and roughly $1.4 billion proving there is now a second real answer, one built from an element abundant enough that no single country or company will ever be able to squeeze the entire industry through it the way lithium has. If this video showed you a piece of the battery world you had not seen coming, hit like, subscribe, and turn on notifications so you catch the next one. And here's a question for the comments. Now that lithium finally has a real competitor built from something as common as table salt, do you think sodium ends up replacing lithium in the cars most people actually buy, or does it just become the second half of a two-chemistry battery industry from here on out?